over weekend.
Oh no, don't be. Hopefully, what you see today will relax you a little bit. I really, really hope so. So let's just get started and see if this will give you a better idea of what I was expecting for those problems. I took a look at the wikis. I didn't comment anything because they're all over the place, and I think we need to standardize something so that it's helpful to everybody. So I sent you this blank form. It looks something like this, where everything you need for any of those problems, hopefully, well, actually, everything you need is here. It's just a matter of knowing what we need. Okay, but essentially, besides some figures that you might need, what I need you to do for any of the groups, for any of the 11 problems, is complete this form. Okay, so just complete this form. I'll show you what I mean by that. So uh, I had a sample. I sent a sample like this. This is for a string problem, or beads, bracelet with beads or something problem, or a polygon problem. All of those are the same kind. And remember that everybody needs to know how to do any of these problems anyways. So this is a sample that I sent. I will say here, this is for strings of any length, or beads problem. Maybe you have different color beads and you're trying to make a bracelet or a necklace, or coloring sides or edges of polygons, um, vertices or edges, coloring vertices or edges of a polygon, or beads to create a necklace or a bracelet, or strings, rotations in word rotations or string rotations. Any of those problems looks pretty much like this one. Any of those you can model with a polygon. Okay, so this example is for a nine letter word, or a polygon with 9 sides or 9 edges, or 9 beads that you're trying to put together to make a necklace or bracelet. Yeah, are we okay with that? So all those problems are equivalent. Everything is going to look exactly the same except for the context, right? So here, what are you coloring? It could be the vertices of a regular polygon with 9 sides, or the edges of a regular polygon with 9 sides, or beads in a bracelet, or words in a string. No? That's what you're coloring. The letters in a string, or letters in a word. So the actual letters take the place of the colors. And so how many objects are you coloring? 9. I have 9 letters, or 9 beads, or 9 vertices, or 9 edges. That's the number of objects that I'm coloring. How many transformations? What kind of transformations? In this example I send you, I have rotations and reflections. And so for a 9-sided polygon, I have, the symmetries of a 9-sided polygon are the 9 rotations. So 360 divided by 9 is 40. So 40 degrees, a 40-degree rotation takes that vertex into that vertex. But I also have 40 times 2, which takes that vertex into that. So I have 9 rotations, right? This vertex can go to any of the others. And the identity. So I usually separate the identity. I have the identity, I have 8 rotations that are not the identity, and then I have the reflections. For each vertex, I have a line of symmetry. So I have 9 lines of symmetry. I have 8 rotations that are not trivial, so not the identity. So 40 degrees and any multiple of 40, 40, 80, 120, 160, and so on. You can count them. And it's 8 of them and the identity. All right? So those are my 8 transformations. So what I have here, that's that. Rotations and reflections, I have 18 of them. And then, whatever I'm asking the problem. So whatever restrictions I have in my problem. For what I wanted for this past weekend was essentially what I'm going to do in this table and maybe, the figures, but only that. So the actual restrictions didn't really matter except for problem 67. And I'll talk about that. So what do we do here? I already told you what the 18 transformations are, and I'm grouping them according to essentially how they behave in terms of the patterns. So the identity, which in any of your problems, because the identity takes any element to itself, and that's the full cycle. It doesn't go out of it. It's just the element, the identity takes the element to itself. Then I'm going to use different letters to label all of the objects that I'm coloring. And so the pattern is always going to look like different letters for whatever number of elements I have. And this applies to the cube, the tetrahedron, to any of the 11 problems in the homework. Okay? So the identity is always going to be just different letters. They don't have to be A, B, C, D. You could use X's, Y's, whatever you want, but 9 different, in this case, 9 different labels. If you're coloring 10 objects, it's going to be 10 different labels. And therefore, the way that I explained to get the monomial, which is actually called a cycle code. So that monomial, the cycle code, remember, this says how many letters appear exactly once. There are 9 of them that appear exactly once. Okay, so that's my cycle code for that transformation. Mm-hmm. Then I have all the other rotations, which in this case are classified into types. I'll explain that, but let me go over the reflections first because those are easier. Okay, so I have the reflections. I have 9 of them, and they essentially behave the same way. That's why I don't do one drawing for each or one pattern for each. I just group them. So there's 9 of them. And then here I wrote this pattern, but what I'm really thinking about is one of these figures over here. Oops. So what I'm thinking about is one of these figures over here. So reflection here, this one over here. So I just take one reflection, whichever it is, and I look at the pattern. Remember, I label my whatever I'm coloring. So in this case, I'm labeling the vertices because I'm thinking about this problem as labeling the vertices, right? So I label them one by one. So at the beginning, you don't have anything. Imagine that there are no letters right now. And so I just pick one of them. So let's pick this one. Pick any label you want, X, P. This time I chose C, right? But whatever label you want, and then see where these vertices go under my transformation. So here I have a reflection. So this letter goes to, this vertex goes to that vertex under my transformation. And if I apply that transformation again, it just goes back to the original. So those two are grouped together in a cycle. And so I just need to make sure that I'm using the same label for those two and only those two, right? And then you look at another vertex that hasn't been labeled and you do the same. So, let me go in order. So I decided to start with this one. Where does this vertex go under the transformation? To itself, right? Because I'm reflecting about this line. So because I already got back to itself, that's the only element in my cycle. So that's the only one that's labeled A. Then I look at another vertex that hasn't been labeled, this one. Remember, this is already done, so that's why I already have all the labels. But if I were doing this now, I look at another vertex that hasn't been labeled. I use a different label. It doesn't matter which one. B. I see where it goes under my transformation. There. I apply my transformation again, back to the original. That closes my cycle. Those are the only two with B's. I do this, take another object that hasn't been labeled, C. Use whatever label different from the previous ones. So C. So apply the transformation and see where it goes. It goes there. Apply it again, but now to this one. It goes back. So that's the full cycle. Those are the only ones with C. And keep going like that, right? So D goes to D and back. That's the full cycle. Another label for the for one of the last vertices. Apply the transformation. E goes to E and back. So that's a full cycle. Yeah. And so the only thing that matters is how many times different letters are repeated. So that's why, this is a picture I have in mind, but I can list all these letters in any order in my table. Okay, so I decided to go in alphabetic order, but again, for the polygons, you can actually list them in the order of the polygon. But when you have tetrahedra or the grid or whatever, in which order you list them, any order you want. But the only thing that's important is that you have the same letters that you had in your figure. So here I have. Oh, actually, I didn't. I decided to go clockwise, or to go in the order of the polygon: A, B, C, D, E, E, D, C, B. So but it doesn't matter in which order you label them. I decided to go like this: A, B, C, D, E, E, D, C, B, and back to A. So A is only listed once. So in any order you want, you list those letters, and then you create the cycle code. So I called it the combined cycle code because I'm actually doing 9 transformations at once. So it's 9 of them. And then what is this? There's one letter that appears once. So one letter that appears once. And 4 letters, B, C, D, E, 4 letters that appear twice each. So that's my cycle code, and that's it. Now, the rotations, there are 2 types of rotations, and these completely depends on the number of sides. So the number of sides here is 9 in my example, and 9 is not a prime. So all the divisors behave differently. The divisors of 9 behave different than numbers that are relatively prime to 9. I'll explain in a second. But that's something, especially you only have like 6, 7, what is it, 6, 7, or 8 letter words, which means the hexagon, the heptagon. So 6 sides, 7 sides, or 8 sides in the homework. So you can as well do it 8 times if you need to. And you'll see that the patterns, some of them are going to be the same, and that's how they're grouped. So here I have, I have 8 rotations total, and it happens that 2 of them actually behave the same, the 120 and the 130, and that's because you're kind of turning like 3 times. 120. Let me show you my figures. So 120, I think a 120 degree rotation goes like 1, 2, 3. It goes here. 1, 2, 3. It goes there. 1, 2, 3. It goes there, and it closes the cycle just with 3 steps. Make sense? And the 240 is the same thing. It's just that it's a 6. So 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So those 2 behave the same way. And all the others actually completely is the same letter for everything. If I go, let's say, by 2s, I start right here. I'll mark them. I start right here and I go by 2s. So 1, 2, I'll go there. That would be like a 80 degree rotation. So, it's 360 divided by 9, that's 40. 2 of them, that would be 80, right? So it's just going like by 2s. I don't really need to know what's the angle. Okay, so I just go by 2s. So I start right there. 2 takes me there. 2 more takes me there. 2 more takes me there. 2 more takes me there. And then I kind of, 2 more after that one is this one right here, right? And then this one, and then this one, and then that one, and then I'm back. So I actually cover the whole thing. And this happens if I jump by 1, by 2, not by 3, because 3 actually closes early. We did that one here, and I jump by 3, right? By 4, but here, by 1, by 2, by 4, 5, by 6, by 7, by 6 the other one, right? By 7, by 8. So that's how I group them in my table. But if you are in doubt of when I actually fill in everything and when I don't, it really is the number, and you already discovered that when, I saw in some of the solutions, you're already looking at the GCD of the jump. Like here I did 2, jump 2, jump 2. For jump 2, what you do is the GCD of 9 and 2 is 1. which means that you're going to cover everything because you are essentially, um, well, you can think of this as the number of times that a letter repeats is 9 over 1, which is 9. In this one, if I have jump 3, the GCD, you don't need to know this, but this is really how things are being grouped. So the GCD is 3, and when I do 9 over 3, this is the size of each cycle. Cycle size. So I have 3 letters, 3 letters in 3A's, 3B's, 3C's. Whereas this one, I have 9A's. Uh-huh. So, anyways, but you don't need to know this. I know that some of you were already thinking about the orbits and how many orbits, and it has to do with the GCD and all of that. But you don't really need to do that. And I want you to think about these problems this way, just with the patterns, because that applies to any single problem. The GCD and all of this doesn't apply to the cube, to the tetrahedron, to the grid. So you will be in trouble. Okay. All right. So, okay. So, here I have, again, the letters listed in any order for most of the rotations. For the special ones, I have 3A's, 3B's, 3C's. I could have listed here, I could have listed these as AAA, BBB, CCC. That's fine. Okay. And then I compute their cycle code, the monomial. There are 6 of them, and there's one letter that appears 9 times. Here I have 3 letters that appear 3 times each, and there is 2 transformations that go with that. So those are my cycle codes. Okay, this column right here and that last row over here is just checking that that things fit, that things may make sense. So the total number of transformations is the sum, right? So we at the beginning we said there are 18 transformations, so I'm just making sure that this is actually 18. Just checking. And this one over here is also just checking for any other cycle codes. So I wrote it here. For any of your cycle codes, when you do the sum of the subindex times the exponent, like here, 1 times 9 is 9. It should be the number of objects that you're coloring. So there are 9 objects that we're coloring here. And so 1 times 9 is 9, 9 times 1 is 9, check, check. 3 times 3 is 9, check. And for this cycle index polynomial, again, we did it before. I have 2 letters. I have ABC. What did I do here? I have one, the A only appears once, and all the others, again, for this one, maybe I'd write it like this. You could also list it like this, right? So I have 1 letter that appears once and 2 letters that appear 4 times. So I can do subindex times exponent, that's 1 times 1 plus 2 times 4, 2 times 4. And this is a 9. Okay. Ha. Something had to go wrong. That's a 9. And that's a check, right? If it had been 8, then something is wrong in all my analysis. It's a check. Yeah? Okay, so that was what I was expecting for this past weekend. That was it. Okay? Let me go over a tetrahedron example. So hopefully, the hardest part on the cube and the tetrahedron is understanding how the behavior of the transformations really. For the grid, it's easier because the transformations of the 3x3 board are just the symmetries of the square. So just 90 degrees, 180, 270, and the 4 reflections. So those are very easy to visualize. But the tetrahedron and the cube are harder because they're in the space. So maybe we'll go over, a table like this for one of each, the cube and the tetrahedron. Let me just, before we moved into that, what's the last stage? That's what I was expecting you to do between today and tomorrow. Okay? So what's the last thing? Why did we do all of this? How are we gonna get to the number of colorings from here, right? This almost seems unrelated. And so this is the actual method. The actual Poviat-Redfield counting method says that you can find these three polynomials. And in my form, I describe how to get them. Okay, so the cycle index polynomial is just the average of the cycle codes, which is the sum of all the cycle codes that you got, the combined cycle codes, divided by the number of transformations. Mm-hmm. So in my example right here, I just add up this, x1 to the 9, 6, x9 to the first, x2, x3 to the third, and 9x1 times x2 to the fourth. So I just add this, and that was a total of 18 transformations. It's just that I have 4 terms because I grouped them, right? I have 6 of them here, I have 9 of them here, but I have a total of 18. So what I have is the sum of these 4 terms divided by 18. That's it. That's a cycle index polynomial, right? Easy. Cycle polynomial, just remove the subindices for the x's. So replace every x1, x2, x3 just by x. Remove the subindices. So that one becomes x to the 9. This one becomes 6x. This one becomes 2x cubed. And this one becomes 9. And then I have x times x to the 4th, so x to the 5th. So just remove subindices. From here to here, you just remove the subindices. Okay? Yeah. And that's also in the blank form, it just, it says this. Just replace every xi by x in that one. So you're just removing the subindices. Okay? Good? All right. So why is this important? The cycle polynomial. So this polynomial is super important because this is the one that gives you the colorings. If you ask me, in how many ways can I color the vertices of a 9-sided polygon if rotations and reflections of a coloring are considered the same? Right? In how many ways can you color with 3 colors? Then you just substitute x equals 3 here, and that's your answer. If you tell me 5 colors, I just substitute x equals 5, and that's my answer. You see? So this method solves a bunch of problems at once, instead of actually doing it by hand, which many of you were trying to do because the number of colors that you are given in these problems is very small. So you can actually try and check, and maybe you are double counting some of them, maybe you're missing some of them, but you're trying to count them, which is great. And you should actually, for some of these problems, especially the ones that give you a small answer, you should try and verify and make sense that, out of the method, like, oh, it really works. Mm-hmm. But the truth is that the method is so powerful because once you get to this polynomial, you have the number of colorings right away. So it doesn't. That's why I didn't focus on the number of colors that you had or anything like that. You see, in my original problem, I said four colors with no restrictions. So my answer to that problem is simply take my cycle polynomial, substitute x equals 4. You see, and that gives me the total number of colorings. All right. Questions up to there? I'm missing one more polynomial, but
just curious, how did you know it was 18? Number of transformations?
That's the number of transformations, and so try to do that at the very beginning because you need to make sure that you have a pattern for each transformation, that you're actually accounting for every transformation here. For the 9-sided polygon is the identity. So there are 9 rotations, right? But one of them is the identity. Then there is other 8, so 9 total. And then there is the 9 reflections. So that's 9 plus 9, 18. So 9 rotations, 9 reflections. But one of those rotations is the identity.
Will it always be just the number doubled?
Or no, no. For the polygons, yes, it's always double for the polygons. But in general, for if you were doing maybe reflections in the space, it's not necessarily. Mhm. Okay, and so
Professor,
yeah,
could you explain the pattern inventory? What does it tell?
yes, that's the one thing that we're missing. But let me see if there are any questions up to here before I go into the third polynomial, which is called the pattern inventory.
I want to know, how do we know the degrees for the rotations? Which one?
The degrees for these degrees for the rotations?
Yeah.
Oh, that comes because we're working with the polygon. The first one is, which is the smallest rotation possible, is a full turn divided by the number of sides. That's 40. And then you have all multiples of 40. Between 0 and 360, because otherwise we are repeating, right? So multiples of 40 degrees. But some of them behave, as I explained, some of them give you one type of pattern, and others give you a different pattern. So you need to kind of figure out which ones are which. Mm-hmm.
Okay.
In the homework, you have 6-sided, 7-sided, and 8-sided. So
wait a minute. Why do you split the two rotations into two different categories, 120 and 240?
And this ones. In this ones, when you rotate, the cycles close earlier. So that's what I was trying to explain here. You see, when you rotate 120 degrees, so let me do this. When you rotate 120 degrees here from the center, 120 degrees fits 3 times in a full turn, right? That's why my cycle closes early. It just contains 3 vertices. Mm-hmm.
Okay, well, can we just list all the rotations into one?
Yes, if you
40
want.
degrees, 80, 120, 160, etc.
Yeah, you can have, if you want, you can have your table with 18 rows if you want. And, some of them are going to be equal. But if you want, you can have one transformation per row. You'll have 18 of them, and you can find the cycle codes for each one of them. Many of them, namely, 9 of the rows, all the ones for the reflections are going to be the same. 6 of the rows for these rotations are going to be the same, and these other 2 are going to be the same. But if you want, yeah, you can list them up. There in the homework, there's going to be 12 transformations for the 6-sided one, or for 6-letter words, or whatever it is, and there's only going to be 14 for the 7 bits in H54, and there's going to be 6. No, what is it? In 58 is 12 because it's 6 bits rotations and flips. Yeah, so it's not that many. You could do it if it's easier for you. Yep. Okay. So third polynomial is the pattern inventory right here. It looks more complicated, but it really isn't. So you're gonna use again. So the cycle index polynomial is the one that gives you the other 2. So think about it as cycle index polynomial gives me my other 2. The first one, which is the cycle polynomial, is the one where you remove the subindices, and that gives you the answers to your problems with no restrictions. And the other one is a pattern inventory, where you're going to replace, I'm going to take my x with the subindex, so x1 or x9 or x3 or x2. Mm-hmm. And I'm going to replace it. Let me go back to my blank formula. I'm going to replace every xi by a1 to the I, a2 to the I, a3 to the I, this sum. And as many terms as colors I'm using. So for this last polynomial, you actually need to use the number of colors that they gave you. Okay, so let me go back to my example. In my example, I was asking for, work with 4 colors, right? So I'm going to use, for the pattern inventory, because this is 4, I'm going to use A1 A2, A3, and A4. Actually, let me do it like this. A1, A2, A3, and A4. Okay? Because it's 4 colors. And I'm replacing, if it's xi, if the subindex is I, so maybe I'll do this. If the subindex is I, then I use that as exponent for each one of them. Make sense? So it's the number of colors, and this is the only of the 3 polynomials that depends on the number of colors that you are using in that problem. The others, we didn't use the colors until the end, right? Just to find the actual answer to my problem. But for the pattern inventory, there is one pattern inventory for each number of colors. Mm-hmm. So because it's 4 colors, I have 4 letters, A1, A2, A3, A4, and each xi is going to be replaced by the sum of these powers, the I powers of these 4 numbers. So x1 is replaced by A1 to the first, A2 to the first, A3 to the first, A4 to the first, which I don't need to write the first, right? So I just write it like this. So this x1 right here, this x1 to the 9 is this one right here. X1 was replaced by A1, A2, A3, the sum of A1, A2, A3, A4. And then I have this one, x9, you see? The subindex is 9, so now I have 9 powers. So is this one right here. See? 9 powers of the same 4, A1, A2, A3, A4. Yeah? And the coefficients and everything else remain there, right? So there's 6 times that, so this is 6 times that sum of 9 powers. And this one was x1 to the 9, so it's the sum of the first powers, everything to the 9. Mm-hmm. And then this one, the 2 remains there, and then I have x3, and the exponent 3 remains there. So I'm really, I'm replacing the x3, I'm replacing the x3, the exponent and the coefficient are exactly the same. I'm replacing it by the sum of the third powers. And then the next one looks a little more complicated. Let me just do soups.
Wait, why is it always A to the 9th power? Like, I get maybe x1 to the 9th because you're replacing each x with an A. But then, like, after the plus 6 times A1 to the 9th power plus A2 to the 9th power, why are we doing all of those?
This subindex sum is the exponent here. You see, like I did over there. The subindex is the exponent. So if it's x9, I'm replacing by 9 powers. If it's x1, I'm replacing by the first powers, right? So I'm not even writing them. I could have written A1 to the first, A2 to the first, A3 to the first, A4 to the first. This one is 3, so 3 is the exponent.
It's gonna be
and
difficult.
Here I have 1, here I have 2, so I'm going to have 2 parentheses, right? So maybe I'll do, I don't know, I don't have any more colors, but I'll do, so I'll do yellow for the x1. So here you have another x1, right? And I'll do blue for the x2. That's powers of 2. The second powers, sorry. Second powers. Because it has subindex 2. And then everything else is exactly the same. So every time that I have an x1 is replaced by the first powers, x9 by the 9 powers, x3 by the third powers, x2 by the second powers. Everything else remains the same. So I still have the over 18. I have the the coefficients that I had earlier, the exponents that I had earlier. I have everything. Everything else remains the same. Make sense? Okay.
I guess I'm just having a hard time understand the powers since it doesn't look like it affects the main computation of the problem, like the four colorings restrictions.
Oh, wait! I haven't told you how to use it, right? I'm just telling you how to construct it. And constructing it is a recipe, right? You don't need to even understand why we're doing this at this point. Right now, I'm actually giving you a recipe. I'm saying every xi in here is replaced by the ith powers of those numbers, a1 through a4, and it's four of them because I have four colors. It's a recipe. I'm not telling you why yet or how we're gonna use it. In fact, I'm not gonna tell you why because we're not actually getting into the details of the proof of this method, but I can tell you how to use it. Mm-hmm. So once you have your pattern inventory, how do you use it, right? So let me go back to my black form here. This is how you use the pattern inventory. So if you know exactly how many times each color is used, the A1, A2, A3, A4 is representing the first color, second color, third color, fourth color. Okay? One per color. That's why we have four. And these M's are representing how many times you want the first color, how many times you want the second color, how many, etc. Right? So that's why this sum of M's is the total number of objects because if you are coloring 9 times, and I have to say like 3 blue, 3 green, 3 yellow. That would be M1, M2, M3, M3, right? So what you do is in the pattern inventory, you're going to find the coefficient of that term in the pattern inventory. And that actually kind of goes back to chapter 1. It's not very difficult and there's not a lot that you have to remember, but this is all we need. Now, if you don't want to do it by, using something from chapter 1, if you don't want to do that, you could, use Mathematica or Wolfram Alpha or any software or that you know how to use or anything on the internet to expand your now you have a polynomial. If you are going to actually use the computer to expand it, maybe use WXYZ instead of A1, A2, A3, A4, and just find the coefficient that you need. But we actually know how to find those coefficients. And that's how I try to explain this over here. So in my problem, in my example, I wanted 4 colorings when each color is used at least twice. Okay, that was my original problem in this example. I'm coloring 9 things, and every color needs to appear at least twice. So the only way that can happen is that if one color appears 3 times and all the others 2 times. Does that make sense? Each color needs to appear twice, so there's one color that appears 3 times and 3 colors that appear twice. So this is what I was saying, right? The M1, M2, M3, M4. Imagine that I told you there must be 3 blue ones and 2 red to green to yellow. If I say that, then it's just going to be one of these terms. But since I didn't specify which is the color that appears the most, then it could be 3 red ones and the others 2 of each, or 3 blue ones and the others 3 of each, or 3 green ones and the other 2 of each, or 3 yellow ones and the others 3 of each. So I need to use the pattern inventory 4 times, one per selection of values of n. But it's going to give me the same. It's going to give me the same for each one of them. So I'm actually kind of focusing on the 3, 2, 2, 2. So I need the coefficient of A1 to the third, A2 squared, A3 squared. This one is 4. This one right here is 4. A4 squared. in the pattern inventory, but now I have it. You see, worst case scenario, if you don't understand this part over here, just expand these and find the coefficient of this term. Expand, combine like terms, find the coefficient of this one, you're done. Worst case scenario. Expand in any way you want, find the coefficient of this. That's your answer. Yeah? But we actually saw ways of computing the coefficient. For example, here, I'm looking for the coefficient of this one. And we saw in chapter 1 that the multinomial coefficient tells you what's the coefficient of this one. It's just the 9, choose whatever combination you have here. So 9 choose 3, 2, 2, 2. So that will be the contribution of these to this term. Now, these ones are all none of this is of this form, right? This is a1 to the 9th, this is a1 to the 3rd, a2 squared. So none of these could be of this form. When you expand that, all the a's are going to have power of 3 or 6 or 9. So none of this is going to be, and you can check it, expand this, and you'll see that none of the terms has this form. So that's why I have 0 of them, 0 of them. And then for this one, I need to get, a1 to the 3rd. I need to multiply this a1. And then when I raise this to the 4th power, I need to get the coefficient of a1 squared, a2 squared, a3 squared, a4 squared, which is this one right here. And I need one of each. That's why it's 4. Choose 1, 1, 1, 1. Times the 9 here, times the one choice that I have here, because I need to use the a1. But again, you can take this, expand it, and find the coefficient of this. So it's just expanding a polynomial, expanding an expression. So you can do it using counting from section 1, but you could also just expand this big polynomial and find the coefficient of that. Right? Questions?
But we have to have it at least twice. So how does that 4 choose multinomial with ones work out in this case?
Well, because we're already multiplying the squares, right? So when you expand this, I'm going to choose a square of a1 or a2 or a3 or a4 from the first parenthesis, right? And then for the second parenthesis, so they already come with their square. Because so I just need to, from my 4 parentheses, I need to select one of each, right? From one of them a 1 square, from another one a 2 square, from another one, So, okay, so probably that's going to be the most complicated part, like this computation, but again, you can just expand these and find the coefficient that you want. And again, if you want to use something like Wolfram Alpha, which is free and it's just like a big calculator, what you can do is, instead of using A1, A2, A3, A4, because it's difficult to work with sub-indices in a calculator, just use X, Y, any letters, X, Y, Z, and W. And you can just say, in Wolfram Alpha, you can say expand, enter your polynomial. And it will give you, it's going to be several rows maybe. And you're looking for the coefficient of the term. In this case, you will be looking for the coefficient of, let's say, x cubed, y squared, z squared, w squared. So just look for that term. And that's the coefficient of that is your answer just for this one, right? And then you multiply times 4. So that's why I have 432 and then times 4 because I have 1, 2, 3, and 4. Now, your problems are easier in this part. But I wanted to give you one example of how you use it. Okay? Questions?
Professor, could you explain the last part of the pattern inventory where we got 9 times 1 times, yes,
This one.
the last part.
Oh, okay. So again, let me instead of doing it with A1, A2, A3, A4, I'm gonna do it with X, Y, Z, W. We're looking for this coefficient. Okay, that makes sense. So that, or I don't know. I'll do it with. See, I have A1 plus A2 plus. I'll do it with the original ones, and then I have A1 square plus A2 square plus A3 square plus A4 square. And I have that 4 times, right? Maybe I'm actually going to cheat. I'm going to copy paste this. Yeah. And so, okay. So this is what I'm expanding, right? For that last part. So I have the 9. The 9 just comes from this coefficient, okay? Okay, so I need to expand this. And one of the terms, is going to be something plus one of the terms is going to be A1 cube, A2 square. There's some coefficient here. That's what I'm looking for. A3 square, A4 square. And then there are many more terms. Agree? I just need to know what is this. And look, when I multiply out, I essentially take, one term from the first parenthesis. I take another term from the second parenthesis. I take another from the first. I take another from the next, and so on, right? I take one term from each of the parentheses. Okay? I'm taking one from each. And that's how I get my terms, right? I need to multiply. When I fold, I need to do this against all of them, against all of them, against all of these, against all of these, against all of these, against all of these. When I fold. Yeah? When you expand this, you need all possible combinations, one from here, one from here, one from here, one from here, one from here. That gives you one term. And then another one from here, from here, from here, from here, from here. It gives you another term. And you need to do all possible combinations, and then you can combine like terms, and that's how you expand it, right? So what I'm saying is that the only way to get one of these terms is I must choose A1 from this one, because all of these already come with the squares, right? So the only way that I can make an A1 cube is if I choose A1 from here and A1 squared from one of these. But then I also need to choose an A2 squared from one of these, an A3 squared from one of these, and an A4 from one of these. Okay? So from here, I'm forced to use A1. So that's where the 1 comes from. So for this one, I need to choose. This is the number of ways of choosing the A1, one way. And then I need to select from my 4 parentheses, I need to select one with subindex 1, one with subindex 2, one with subindex 3, and so on. So from my 4 parentheses, I'm selecting one with subindex 1, one with subindex 2, one with subindex 3, and one with subindex 4. So this is choosing an A1 square, this is choosing an A2 square, like from which parentheses it comes from, A3 square and A4 square, from those 4 parentheses, and this is selecting an A1. But again, this is from chapter 1. So we did this kind of thing from chapter 1, and we did it a long time ago. So the simplest thing to do is to actually expand it if you want to. Okay? You can actually expand it. So that's why I said instead of working with the subindices, expand x plus y plus z plus w times x to the x squared, y squared, z squared, w squared to the 4. Expand that, and one of the terms is going to be x cubed y squared, z squared, w squared, you're looking for this coefficient. And it's going to be that one. This is just for factorial. This is 24. So this is 24. Expand this and look for the coefficient of that one, right? So do it actually, you can enter it in any, go to Wolfram Alpha, enter this, and you're going to see that the coefficient is 24. Okay? All right. Okay, so that's like the last technical part, but it really, the idea is that if you have a calculator, if you have some kind of system that can expand multiplications of polynomials, you're done. It's just that coefficient. Mm-hmm. Okay, so let me just now go over something about the cube and something about the tetrahedron to help out the groups that have cubes and tetrahedrons, right? And hopefully the rest you can complete, but we still have Thursday. So let's go over, let's say for the tetrahedron, an example that's related to the tetrahedron. Let's say that we want to color let me just make sure. So in the homework, you have edges and you have the pyramid with the 10 balls. All of those are done with the same transformations. Those two problems, 79 and 80, are done with the same transformations, okay? So in this example, I'm going to color the vertices. Let's say that I'm coloring the vertices of a tetrahedron. Okay, and in the space, everything is only rotations in all of the problems. So I'm only going to do rotations. The tetrahedron has 4 vertices, so I have four objects to color, and I have 12 transformations. 12 transformations. I'll tell you what they are. So I have the identity, and the rest depends on the problem. But let me focus on this part. So I have the identity, as usual. And then for the tetrahedron, I have So I have this type of rotations where I'm just kind of spinning from the top, right? I call them vertex to face. Vertex to face. Because the rotation axis goes from one vertex to the center of the face, and that's where you spin, okay? I have 120 and 240. I have, three rotations, but one of them is the identity. So I have the 120 and 240 rotation. So let's say if you start like this, you see the blue and green, then I can rotate and see the green and orange. And then that's 120. And then I have orange and blue, that's 240. And then I'm back to green and blue. Okay, so it's the identity that's already in the first row. And then 120 and 240. And I also have the edge to edge, what I call the edge to edge rotations. And this is 180 degrees. So those are the ones where you place one of the edges on the table, right? So one of your edges on the table. And then you would center, so you have the opposite face also parallel to the table, right? Or, let's do it like this. So one of my edges on the table, and then I have the top edge, that's right here, horizontal, parallel to the table. And then I have the rotation that goes, this edge kind of rotates 180 degrees. So you can do that. See? So that's the rotation I'm talking about. And I have one rotation per pair of opposite edges. So this one goes with the one that's under this. And I have 6 edges total. So, I have 3 pairs because I have 6 edges total. I have 3 pairs. So I have 3 of this. And for the vertex to face is 1 per vertex, right? So 4 of them, one per vertex space, per vertex space. But then I have 2 of them because it's 100. So this is 120 degrees and 240 degrees. That's why I'm multiplying times 2. And this is 1 per vertex. Make sense? So I have 8. I have 8 of them. I have 3 for the edge to edge. So this is 3 pairs of opposite edges. That's my 3. And then the identity is only 1. Right? And what are the patterns? Well, I'm coloring, and that's why I wanted to have this here. I'm coloring, vertices. Okay, so I'm coloring vertices. I have 4 of them. I have the top and these 3. So I have four vertices. And so for the identity, as I said before, it's just going to be 4 different letters. Let's say A, B, C, D, 4 different letters. And so the cycle code is number of letters that appear once is 4. Then for the face, vertex to face, I'm coloring vertices. Right? So this vertex goes to itself when I spin, right? So I'm just gonna have one vertex that goes to itself when I rotate. You see? This vertex goes to the top vertex goes to itself when I rotate 120 degrees or 240. You see? And what happens with the other vertices? I have 3 more. And when I rotate 120 degrees, this one goes to that one, and this one goes to that one, and then I go back to the original one. You see, I started with orange blue, right? I rotate once, it goes to orange green. I rotate another time, it goes to green blue. And I rotate another time, I go back to my original orange blue. Okay, so those 3 vertices on the base are in the same cycle. One goes to the other, one goes to the other. So that, if you want, that would be like A, B, B, B. You see? And so my cycle index it's 8 of them. I have 1 letter that appears once, and I have 1 letter that appears 3 times. 1 letter that appears 3 times. Right? And then for the edge to edge, here, so you see orange. When I rotate 180, I do see blue. But I need to follow the vertices because I'm coloring vertices. For the problem for your coloring edges, this edge remains the same. So remember, if you're coloring edges, you can label your edge A, and A goes to A. The bottom one goes to itself as well. If you were coloring edges, if you're coloring the spheres, the 10 spheres in problem 80, imagine you have 1, 2, and 3 bolts right here. 1, 2, and 3, right? Because it's a pyramid of, you have 1 ball on top, you have 3 in the next, and then in the next row, and 6 on the other one. So if you turn it like this, you have 1 ball here, 1 in the middle, and 1 there. And when you rotate, you want to see this ball goes to that one, and then you rotate again, it goes back to that one. So these 2 get the same letter, and the one in the center goes to itself. So that would be like an A, B, and B. And then what happens to the others, right? You're going to have, that's what you need to figure out, okay? How many are grouped together? The ones on the bottom, same thing. The one in the middle, this one right here in the middle, goes to itself. So it's another letter that's by itself. And the 2 that are on the opposite corners right here, they go to each other. So that's another pair to have, like A, B, B, C, D, D. For edges, this is A, it goes to itself. This one on the bottom is B, it goes to itself. And now you need to figure out where this one goes to, this edge right here, where it goes to when you rotate 180. It's going to go to an edge here on the back. But you need to actually try to visualize it, okay? All right. So yeah, I was doing vertices. Sorry. So I was doing vertices. So this vertex goes to that vertex and back, right? So that's I'm gonna write that as AA. You see, this vertex goes to that one and back when I rotate like that, and then back. And the two vertices on the bottom, this vertex goes to the back and then back to the original, to the back to the original. So this is BB. Mhm. So this is 3, and there are letters showing twice. There are 2 of them, and that's it. You can do, this is the hardest part, because now this is just checking that everything makes sense, checking that here 1 plus 8 plus 3 is actually the 12 transformations. And then you can find your cycle index polynomial, your cycle polynomial, x1 to the 4 plus 8x1 x3 plus 3x2 squared divided by 12 transformations. So I just add that divided by 12, yeah? And for the other one, I remove the sub-indices. And so this one is just x to the 4 plus 11x squared over 12. Mm-hmm. And so if you ask me, if I give you some number of colors, 3 colors, maybe 3 is too many, 2 colors. In how many ways can I color the vertices of the tetrahedron using 2 colors if rotations of the tetrahedron of the same coloring are considered the same, right? I just substitute 2 here. So for my general problem here with 2 colors, so if I use k equals 2, my answer would be 2 to the 8 plus 11 times 2 squared divided by 12. That would be the total number of colorings of the vertices of the tetrahedron with 2 colors where rotations are considered equal. Mm-hmm. Now, pattern inventory, I have that A1, X1. I said 2 colors, right? So 2 colors here. So I can use A1 plus A2. Yeah. And so each xi, so each xi is replaced by A1 to the I, A2 to the I. So my pattern inventory, I go back to this original one, right? So I have A1 to the A1 plus A2 because the subindex becomes the exponent to the 4. X1 becomes A1 plus A2 plus 8, A1 plus A2, and then the third powers. The subindex becomes the exponent.
Professor, quick question.
Yes.
For the no restrictions colorings, how'd you get 2 to the 8th?
2 to the thank you. 2 to the 4th.
Okay.
Whatever I had in my polynomial. Thank you. Let's see. So I'll do it with red so that I changed it. Thank you, Victor. So whatever my polynomial was, right? I just substituted 2. Thanks. Okay, and then for the last one is 3x2 squared. So I still have the square. The 3 and the square remain there. And then the x2 is replaced by the a1 plus a2. And all of them have a square because the subindex was 2. And then don't forget to divide by the 12. That's your pattern inventory. So if you ask me for number of 2 colorings, so using for number of colorings of the vertices of the tetrahedron, with 1 blue and 3 red. right? So I have 4 vertices, and I'm actually telling you how many of each, right? My pencil. I hope it lasts 9 more minutes. So if I told you what is this, I'm going to use M1 equals 1. I'm going to use M1 equals 1. It doesn't matter, right? It could be M1 equals 3, M2 equals 1. I can reverse these. But, yeah. So I'm looking for the coefficient of A1 to the first, A2 cube. Yeah. So my M values, these ones, are my coefficients here. Yeah, I mean my exponents. Yeah. So that's this is a 1. It's the number 1. Yeah. So I'm looking for the coefficient of that in the pattern inventory. In that one. So worst case scenario, expand that and find the coefficient of A1 times A2 cube. Yeah? Okay, questions?
Oh, I have a question. How did
Yes.
we get A, B, B, B on the second row, vertex to the face?
Oh, so in the tetrahedron, you're gonna rotate, this is the rotation edge to edge. So you can place it on the table, maybe like this, right? You can place it on the table and then rotate 180 degrees. So like that. And then you need to follow the vertices. So if I start like this, right, and I rotate 180, let's follow this vertex on my right. I don't know. So this one here. If I follow it and I rotate 180, now it's on the other side. It's over here.
Professor, it's
And
vertex
then it goes back. What was that?
Vertex to the face, 120 and 240 degrees.
Vertex to face add rotations like this. Like this. You see? In these rotations, this vertex goes to itself. That's why we only have one A. So that you can label this A and the other 3 B. Whereas in these rotations, you can label these 2 A's and these 2 on the bottom B's because they go to each other. A's goes to A's, A's go to A's, and B's go to B's.
Oh, okay, got it. Thank you.
Right?
That makes sense. Mm-hmm.
Okay. So, very quickly, rotations of the cube. Okay? For those that have cubes, those are easier to visualize. That's why I wanted to go over the tetrahedron, because cubes are easier to understand.
I may have a cube at my grandfather's house, but I don't know about the tetrahedron.
Yeah. Oh, I'll send you a link. I'll send everybody a link. Did I send that to you, Scott, when you asked me? Did I send you a link to visualize the tetrahedron?
The Wolfram Alpha link?
Yeah.
Yeah.
Were you able to see something? Or what?
I'll be honest.
It wasn't very helpful.
I didn't get a chance to plug it in, yeah.
That's all right. So I'll send that link to everybody so that's another way to visualize it. You can also Google, rotations of the tetrahedron, and maybe there are some animations out there for sure. Okay. So here, the cube. I have 24 rotations. Okay. For any of the problems, any of the 4 problems related to the cube, this is for the cube. It's rotations only. For any of the problems in the homework, it's rotations only. There are 24 of them. And as I said last time, depending on which of the 4 problems you're working on, you are coloring vertices, or you're coloring edges, or you're coloring faces, or you're coloring the little squares in a 2x2. So this is a 4x4, but in a 2x2, you're coloring the little squares like this. Or you're in a 3x3, the last problem for the cube, I think it was 7. You're actually coloring, imagine that these are like Legos. You're coloring the full little cubes, okay? 26 of them in a 3x3 by 3. So 3 by 3 by 3 is actually 27 little cubes, but you don't count the one in the center that you cannot see from the outside.
If it's a 3 by 3 cube, wouldn't it be 9 little cubes on each face, basically?
Yeah, so 9 plus 9 plus 9, right? Because you have the 9 in front, the 9 on the back, and the 9 in the middle. That would be 27. So 27 little cubes. But the one in the center of the cube, you cannot see from here because it's surrounded by the others. So that one we're not coloring in problem 77. Okay. So rotations. You have the identity. There's only one of them, and you know how to handle that one. And you have what I call the face-to-face. For this, you have the 90 degrees, I'll show you, and the 270 degrees, and also the face-to-face, the 180 degree rotation. So face-to-face, you place one face on top of the table, the other one is parallel, and you're just rotating like this. Okay, that's face-to-face. Now, the one that rotates 90 degrees or 270 will have the same pattern inventory. So you could just do 90 degrees. The one where you rotate 180 is different. So for example, if you are rotating around this face, if you rotate 180, these two corners get the same letter. And these two corners get another letter like A, A, B, B. But if you only rotate 90 degrees, you're going to have all of them being A's. So that corner goes to this corner, goes to this corner, goes to that corner. So rotations like this of 90 and 270 behave the same. 180 is different, right? Okay. And so here I have 6 faces. So I have 3 pairs of opposite faces. Top, bottom, front, back, side, side, left, right. So I have 3 pairs, and I have 2 angles. So these are 6. So that's the angles and pairs. Angles, 90 and 270, and these are pairs of opposite edges. Opposite faces. So there are 6 of them. Okay, then I have and this one face-to-face is the same thing. It's 3 of them times 1 angle, right? 3 times 1, just 1 angle. So far I have 10, I'm missing 14. So I have the vertex to vertex. Let me list them. Vertex to vertex. And I also have the 120 and 240, I'll explain. And I have the edge to edge, 180 degrees. And so let me start with the vertex to vertex. You place one vertex on top of one vertex on top of the table, and there is another vertex that's opposite to it. Like, I don't know if you can see this. Yeah. And then you spin right there. Okay? Just spin right there. So like this edge goes to that edge, goes to that edge. These are 120 degrees because I only have 3 edges around. So 120 and 240, and they behave the same. So that's vertex to vertex. Okay? And the other one is edge to edge. This is similar to the one for the tetrahedron. Here you have one edge standing on the table, and then right above it, another edge that's parallel to it, like this. And then you rotate 180 degrees. So you see, blue, orange goes to, it was blue, red. Blue, red, no. This is red. So maybe I'll do it with different colors. This one, like this. So green, white goes to blue, yellow, and then back to green, white. You see? And these lateral faces go to each other. So here, this one, 180 goes to that one. You see? Okay. So for this one, there are 6 of these because I have 12 edges and I'm taking pairs of opposite edges. And for this one, there is 8 because I have this one, there's 8. Oh yeah, let me write it like this. I have 4 times 2. So I have 2 angles and I have 4 pairs of opposite vertices. And these are pairs of opposite edges. Okay, and now you have to label them. So just track when if you're doing this pin with one vertex, whatever you're coloring, you have to track. If I'm coloring edges, where this edge goes when I rotate 120, the 3 edges around this vertex will be grouped together. If it's faces, the 3 faces around this vertex will be grouped together. Mm-hmm. If it's little squares, these 3 little squares around this vertex go to each other. That's a cycle. And then the next 3, they're gonna be grouped together by 3s. Mm-hmm. If you're doing this spin, this corner goes to that corner, this edge goes to itself, this face goes to the back. And so depending on what you're coloring, you can label, right? If you're doing this one, same thing. This face remains itself, but if you're coloring things on top of that edge, you need to figure out, this corner goes to that corner, this corner goes to that corner, or what is it, depending on what rotation. And that's where the dividing into levels might help you. All right? Okay. All right. So try as much as you can for each of your problems, complete this page. Okay? So for each of your problems, complete this page. If you want, if it's easier for you, instead of the wikis, you can send me this page completed by hand on the computer, whatever it is. Because I think at this point, I don't want you to spend time typing. I just want you to solve the problems. So just complete this page by hand if you want. Take a picture, send it to me anytime tomorrow. All right? And then I'll have answers, full answers for you on Thursday, and you can ask me questions about that. And, those are the 11 problems to prepare for the exam. Okay? Yeah.
Professor,
Okay.
I have a question. So we're going to, for our groups, we're going to be doing, filling out this sheet for our wiki problem that we did. Yeah. Okay.
Yeah.
And then
so in replacement of the wiki problem, so that you don't spend that much time, just complete this page. Go ahead.
Okay, so when everybody else finishes theirs, are we going to be able to see everybody else's or no?
Yeah, so what I'll do is I'll complete the 11 pages, 1 page per problem. I'll have the PDF ready. I'll make it available Thursday morning.
Okay.
And you need to send it by email, send me this page completed. So instead of working on the wikis and spending time on the wikis, it's good for communicating with others, but I think at this point it's easier to just work with the form, send it to me by my email anytime today, tomorrow, and then I'll have full solutions, 1 page per problem, available as a PDF file Thursday morning.
Okay.
All right?
Awesome. Thank you.
All right. No problem.
Professor?
Those will be my solutions. Yeah.
Sorry, would you mind complete this table for cube and actually post it on the canvas like how you did for tetrahedron?
Yes, so I will do that. I will do it for a problem that's not in the homework as I did for the tetrahedron. I'll complete this one and I'll have it as a sample for you. Definitely, I'll do that.
Okay, thank you so much, Professor.
It's just going to take me a little longer to upload the notes today, but I will include it.
Do you
Okay?
have
Thank you.
office hours today at 2:00?
Yes, I'll be there.
Okay.
All right.
Thank you.
Okay. You're welcome. See you guys.